The last part to the bonding unit is going to be intermolecular forces. Intermolecular forces versus intramolecular forces. Intramolecular forces are what is holding the molecule together as form of a bond, okay, between oxygen and hydrogen. This covalent, single covalent bond is an intramolecular force. Intermolecular forces are forces of attraction between the molecules themselves. The first one that we're going to mention is the ion dipole. The forces of attraction between any ion and a polar molecule. For example, if I put salt in water, okay, and remember, if I put salt in water, I'm going to have Na over here, and I'm going to have Cl over here. And look at the water molecules. They're aligning up so that the negative end of the polar water molecule is facing the positive end of the cation, and vice versa over here. This is called an ion dipole attraction. This is what it would look like: sodium, water, chloride, water. A dipole-dipole attractive force is between the negative end of a polar molecule and a positive end of a polar molecule, such like this. So polar molecules will experience dipole-dipole forces. Some polar molecules can experience something called hydrogen bonding as well. It is a type of dipole-dipole attraction. It only occurs if a molecule has hydrogen in it, number one, and it has to be bonded to either fluorine, oxygen, or nitrogen, NOF. And they are 5 to 10 times stronger than a typical dipole-dipole attraction. Why are hydrogen bonds so strong? Well, first of all, they're one of the most electronegative elements that we have: fluorine, oxygen, and nitrogen. And they form very, very, very polar bonds. These atoms are very, very small, highly electronegative, and so they concentrate all the electrons on that element. Also, they have lone pairs on fluorine, oxygen, and nitrogen, which increases the negativeness to that side of the molecule. So here I have a water molecule, which is polar. Here's another water molecule that's polar. This right here is a hydrogen bond. If I have water right here with other water, okay, it can form a hydrogen bond, but this right here is methanol. So now I've got methanol inside water, an alcohol in water that forms hydrogen bonding. This is acetamide, and if you'll notice, this is one molecule of acetamide. Here's another one. This forms 2 hydrogen bonds. Okay, so it's twice as strong. Its boiling point is even higher. Ethanal does not form hydrogen bonding because I don't have hydrogen bonded to a carbon, or excuse me, to either oxygen, nitrogen, or fluorine. Okay, I have an oxygen and I have a hydrogen, but they're not bonded together, so therefore there's no hydrogen bonding. Okay. As we go down a group on the periodic table, whether they have hydrogen, hydrogen, and hydrogen, and hydrogen, as I go down the group, their boiling points go up. I'll explain that in just a second, but notice that the only 2 up here that have the freakishly large boiling points are the ones that experience hydrogen bonding. An ion-induced dipole is if I have an ion like sodium +1 and a nonpolar species. Okay, nonpolar species still have electrons, they still have protons, so therefore this negative right here, this electron, is going to be attracted towards that ion right there. So I can take a nonpolar substance and all of a sudden polarize it. A dipole-induced dipole is when I take a polar molecule and a nonpolar molecule. Okay, polar molecule, has a slight positiveness and a slight negative charge to it, and therefore this electron will be attracted towards the positive and vice versa. London dispersion forces are the weakest of all the forces. These forces exist between all species. All things experience London forces. They contribute to the overall force of the attraction between all particles. London dispersion forces are the only intermolecular forces that keep nonpolar species held together. Okay, what does this mean? Well, first of all, if I take something like hydrogen, hydrogen has 1 proton, 1 electron. Okay, at any given point in time, like if I just freeze it, it's going to be polar. I've got a negative end and a positive end. Negative end, positive end. Negative end, positive end. Negative end, positive end. That's an instantaneous dipole. Okay, but if I average it all out, okay, because electrons are moving really, really fast, then overall it's nonpolar. There's an even charge distribution. Okay, so this is a nonpolar molecule, atom, if you will. But at any given point in time, I can have an electron right here. Okay, well, if I have an electron right here, that means that this guy right here is going to be attracted towards it. Well, that's your London forces right there. Okay, at any given point in time, there's going to be a slight attraction for the positive to the negative of another atom. Okay. As we go down on the periodic table, the larger they are, the more polarizable is what we say. They have more electrons. Iodine has a ton of electrons, and therefore there's more chances that the electrons are going to be on one side of the atom a little bit more than the other, and therefore we call it more polarizable. Larger species with more electrons are more polarizable. They have a weaker hold on their outer electrons. If you go down a group, there's more electrons, therefore it's larger, therefore it's more polarizable. Okay, so the strength of these forces. First of all, actually up here you should have your metallic forces, because those are the strongest. Then an ion-ion force, that's an ionic bond, NaCl. Then you have an ion dipole force, which is like sodium ion in water, or chloride ion in water, a polar molecule. Then with the polar molecules, hydrogen bonds are the strongest, then just dipole-dipole forces. Then an ion-induced dipole, that would be an ion of like sodium +1 and a nonpolar molecule. Dipole-induced dipole is when you have a polar molecule and a nonpolar molecule. And then London forces is when you have a nonpolar molecule and a nonpolar molecule. So ionic, and a polar. This is polar with hydrogen bonding, hydrogen and nitrogen, oxygen, or fluorine. Dipole-dipole is between a polar molecule and a polar molecule. Ion-induced dipole is when a nonpolar and an ion are in contact. Dipole-induced dipole is when a nonpolar is in contact with a polar. And then London forces is when you have a nonpolar in contact with another nonpolar. Okay, so which species has the higher boiling point? Well, first of all, these are both nonpolar. So what kind of forces do they experience? London forces only. Okay, which one has the higher boiling point? Well, this guy weighs more and therefore has more electrons, therefore is more polarizable. Okay, how about these two? Which one is going to have the higher boiling point? Well, first of all, this is nonpolar. I'll explain polarity in class to straighten that out in just a second. This right here is going to be polar because it has an uneven charge distribution. Okay, so polar, nonpolar. Remember, nonpolar molecules only have London forces. This is going to have London forces. It's also going to have dipole-dipole forces. Matter of fact, it's also going to have, look right here, hydrogen bonding. Okay? So therefore, this is going to have the higher boiling point, 78 versus negative 42. How about this one right here? This one is polar. That one's polar. This has hydrogen bonding. This has hydrogen bonding multiple times. So they're both polar. They both have hydrogen bonding and London dispersion forces, but this has twice the amount of hydrogen bonds. It's also larger, therefore more polarizable. Therefore, its boiling point is 188 versus 66. This one right here, nonpolar. Nonpolar. So what's the difference? They both have London forces, but this one's bigger, this one's more massive, there's more electrons, it's more polarizable. Therefore, it's going to have a larger melting point. This is ionic. This is polar covalent. Remember, ion-ion has the strongest intermolecular force. This is ionic bonds versus covalent hydrogen bonds. Look at its boiling points compared to water.